No.
All right, so I am recording now, so I'll post this later for everybody to look at. I forgot to record it in the 8 o'clock class, but I'll record the 9 o'clock session, same thing, and you'll be able to go back and look at this later. All right, I'll give you about another minute to answer the question in front of you, and then we'll discuss. All right, about another 10 seconds. If you haven't responded, please do so. All right, everybody that's logged into Learning Catalytics has responded. So let's take a look at the results. The results on this problem show 47% of you correctly identified answer choice B. That is the only correct answer on this problem. We'll talk about how there are more than one correct answer to this question, but only one of the correct answers is actually shown here. So, you know, this is just sort of playing a matching game. It's similar to the problem we ended class with last time. I'm matching a couple of things. So first off, things that are in the same location in both problems must match up. In particular, I'm looking at this piece right here where I have an a plus h and a 16 plus h inside the function. So that tells me right away that a plus h has to be 16 plus h. Well, it doesn't have to be, but it's very likely that it is. And so that tells me that a is 16. So I already have my suspected a value. And there's only one of them in the problem that has a equal to 16. So it's a good bet it's that one, which it turned out to be. But there's another point of comparison here. If you look at the green highlighted section, you've got f of a, which we now think is 16, should be 2. So if f of 16 should be 2, you know, kind of immediately I'm thinking, okay, looking at the function that I have here, that looks like the fourth root of something. So if I say f of x is the fourth root of x, then that implies that f of 16 is the fourth root of 16, and the fourth root of 16 is indeed 2. So that checks out. So we've got both pieces that we need. We've got f of 16 being equal to 2 checks out. And so we know that it's the fourth root of x evaluated at the point 16. So our function is fourth root of x, and this is occurring at the point x equal a equals 16. Now, I want you to understand that when you do a problem like this, it's almost always going to be a multiple choice question. And the reason it's going to be a multiple choice question is because there's more than one answer to this. For instance, if I had chosen f of x to be the function, the fourth root of 16 plus x instead, and I said that we were calculating the derivative at a equal to 0, that would still work, because f of 0 would be the fourth root of square root of 16, which is 2. That checks out with the formula. But then also f of a plus h, which is f of 0 plus h, or just f of h, is the fourth root of 16 plus h, which also checks out with the formula. So this formula can represent multiple derivatives being taken at multiple points, but all that you're really doing here is shifting the function. For example, if you look at this pairing, how is it related to this pairing? So taking the derivative of the fourth root function at 16 is the same as taking the derivative of the fourth root of 16 plus x at 0, because this function and this function are identical, except this one has been moved 16 places to the left to give this one. So they're essentially the exact same graph. It's just been shifted to the left by 16 units. And so you can always like horizontally shift a function, and that doesn't affect the slopes of that function. So it doesn't affect the limit formula for the derivative of that function. So this is why this was a multiple choice question. You can say that this represents the limit of many different functions being taken at many different points, but they're all horizontal translations of one another. All right, hopefully that was helpful in kind of running down, matching the formula with a derivative that's being taken there. So this moves us on to the algebra heavy part that I was talking about earlier. We're going to have to be able to calculate derivatives algebraically on this first test. Beyond this first test, we'll have better ways of handling derivatives, simpler ways of handling derivatives. But for this first exam, we are going to look at derivatives through the limit definition of the derivative. And I promise you, you'll have to do a problem like this on the exam. So you're going to want to devote some study time to this, look at plenty of examples. There are some videos that go along with today's lecture. There are some extra notes that go along with today's lecture. So please be sure to take a look at those. All right, what are we trying to do? Well, I want to come up with a formula for the slope at every point. And that's what the function f prime is. F prime gives me a formula for the slopes on the function square root of x, which is the derivative I'm going to calculate here. Formula for the slopes of square root of x at every x value. So I can be anywhere on the square root function, and this f prime function that we're about to calculate, the derivative, tells me the slope when I'm at that point. So it's simply a function that collects data on rates of change. That's what we're calculating here, is the formula for the function that stores rates of change information. And our definition from last time is that this is the limit as h goes to 0 of f of x plus h minus f of x all over h. And this formula needs to be memorized. There's no way around it. You need to know the formula or else you can't do the problem. And I would recommend you do a lot of these. There's going to be a couple of them on the homework, but sometimes they can be a little long. So I tried not to put too many of them on the homework assignment. But there are going to be some on the homework, and there'll definitely be some on the skills quiz. So make sure you give this plenty of practice. All right, so I would recommend you kind of come off to the side here. So that's what I'm going to do. I'm going to say, okay, my function is the square root function. I know I'm going to plug that in right here. But I've also got this piece here that I need to update the formula with. I need to tell what f of x plus h is. So this is the way that function notation works. If f of x is square root of x, then x is just a placeholder. It just says, this is the input, right? So the input here is inputted here as well. It's copied, right? Whatever goes in here is copied to here. So f of x plus h gets copied to where x normally would be. So this is square root of x plus h. So that is the other piece here that I'm going to line up in the formula. So the formula is the limit as h goes to 0 of square root of x plus h minus the square root of x all over h. And you can see that I've lined up each of the pieces here for this problem. Most students that do this step correctly get the problem right. If you can simply set up the limit correctly at the beginning, most students will carry the problem through to the end correctly. And the reason is because we've been practicing limits. And at this point, that's all this is a limit problem. I'm just calculating a limit at this point. And so if you look at this limit, you say, okay, I'm going to try to directly substitute first, see if that works. By the way, it never will for these definition of derivative problems. But if I try to plug in h equal to 0, I get square root of x minus square root of x divided by h. Well, h is 0, so that would be divided by 0. So that's 0 minus, or that's square root of x minus square root of x is 0 over 0, which is indeterminate. So I get nothing by directly substituting. Okay, let's do some algebra instead. The algebraic technique here, we've seen this several times in the course, is to multiply by the conjugate. So if I multiply by the conjugate, it's square root of x plus h plus square root of x over the square root of x plus h plus the square root of x. So I multiply by the conjugate. All right, we've talked about before with conjugates, if you have something of the form a minus b and multiply it by a plus b, the result is you square the first term, square the second term, and subtract. So let's do that algebraic step in the top. If you square the first term, that's x plus h. If you square the second term, that's x, and we subtract. In the denominator, you should just keep everything as is. Don't try to FOIL it or combine it in any way. In the bottom, you have h times square root of x plus h plus square root of x. Now, you should be mostly comfortable at this point with what I've done here, because we've done this 3 or 4 times already this semester with taking conjugates and doing limit operations. If you look in the numerator here, I've got x minus x cancels, leaving me with just an h in the top. And the h that's left in the top will cancel with the h that started off in the bottom. Now, here's the moment that you'll be working toward in every single one of these limit problems. You'll be working toward the moment where you can cancel the h that was in the denominator from the very beginning. We're not going to get anywhere unless we can get rid of that h, because if we can't get rid of it, we'll always be dividing by 0. So the algebra steps that you do on these limits will always result in a step like this occurring, where the h in the denominator cancels. That's how you know you're doing it correctly. All right, if I do that cancellation, I'm left with nothing in the top, which means I'm left with 1. So I'm left with 1 in the numerator. And in the denominator, square root of x plus h plus square root of x. All right, now's the time to directly substitute again. If I substitute in h equal to 0, I've got a square root of x here and a square root of x there, which means I have 2 of them in the bottom and a 1 on top. And that is the correct answer. So what we found on this problem is if f of x is the square root of x, then its derivative is 1 over 2 square root x. That's the pairing that we've made. So a way to think about this is this function gives me position data, and this derivative gives me velocity data, right? Tells me the slope and direction at every point. For instance, if I was looking at, say, x equal to 4, then I know my position, my function gives me a position of square root of 4, which is 2, right? I can think of this as position. But the derivative gives me 1 over 2 square root 4, which is 1/4. I can think of this as velocity or rate of change. So that's what this formula is giving me. It's giving me the velocity associated with a position somewhere on the graph. All right, I'm going to pause for a second because we did a lot of work there. Do y'all have any questions about the procedure that we followed here? Starting with the formula that needs to be memorized and working our way toward the final answer. Any questions? Okay, it looks like y'all are good. All right, let's move on to talking about taking another derivative. So what we just took was what's called the first derivative, because we're calculating the first rate of change at every point, which is the slope. But slopes can change. So you can have slopes of slopes, right? In the real world, we would call that something like acceleration, right? Acceleration is the second derivative of position because it's the rate of change of your velocity. So we need some notation for that, and we need to be able to calculate them. So let's talk about the notation first, and then we'll do a calculation together. So this is notation for higher derivatives, because it turns out you can take more than just 2. You can take as many derivatives as you want. Some functions have derivatives of all orders. So if you recall from class on Monday, we talked about 2 different notations for the derivative. You've got the Leibniz notation, which is the derivative of f is df dx, right? It's this ratio of infinitesimals. Then you've got the Newton notation, which is the derivative of f is f prime. It's the function that's derived. Well, what does a second derivative look like for each of these? Well, a second derivative would just be the derivative of the derivative. That's how we define a second derivative. You're taking 2 derivatives. And the Leibniz notation for that is actually really clever. You think of the d here in the derivative operator as being a differential. So d times d is d squared of f. And in the bottom, you have dx squared. You're taking 2 differentials of x, so that's dx squared. Now this squared here is actually on the dx, not on the x, right? So the dx squared is actually dx squared like that. It's just nobody writes the parentheses in the notation. So that's how, using Leibniz notation, you would notate a second derivative. What about Newton's notation? Well, Newton's notation is the derivative of the derivative, but if you've already taken the derivative, right, we know the derivative is f prime. So it's the derivative of f prime, which is f double prime. Use a second prime notation to indicate you've taken the derivative twice. All right, if I did a third derivative, this would be the third derivative of f with respect to x 3 times. And down here, it would just be f triple prime. What about a fourth derivative? Now, the reason I even bring this up, we're not going to do many calculations this semester that involve a fourth derivative at all. Third's about as high as we typically go. But if I was to do a fourth derivative, what would the notation be? For Leibniz, it's pretty straightforward. That's the notation for a fourth derivative. But here, you can kind of sense with the Newton notation that if you were to continue doing this, at some point it would become absurd. Like if you were doing the 100th derivative, can you write 100 tick marks or 100 prime marks superscripted there? No, you wouldn't want to do that. So beginning with the fourth derivative, you place the number of derivative in parentheses as a superscript. So this represents the fourth derivative of the function f with respect to x. This is not to be confused with power. So f, if I just wrote f4, this is the same thing as the fourth power of the function f, which is f times itself 4 times. So this is not the same as this. The parentheses are what set them apart. So if you put parentheses around a power, you're actually notating a derivative mathematically using Newton's notation. All right, with those notations set, what I want to do is pick up the problem that we started here. So we found the first derivative, 1 over 2 square root of x on the previous problem. I want to take one more derivative. So I want to find the second derivative of this function. Now, this is going to be a little bit more difficult than finding the first derivative. There's only one type of function, well, technically two, but really one that we see a lot of that gets easier the more derivatives you take, and that is a polynomial. It's why in high school, most of the examples you get in a calculus course are polynomials, because polynomials get easier the more you take the derivatives. Most other functions do not. Most functions get more difficult the more derivatives you take. So I wanted to start off with a medium difficulty problem to look at. We could have started off with polynomial. We're going to do a polynomial here in a little bit. But I wanted to show you that if you're going to do these problems by hand, which eventually we're not going to, but if you're going to do these problems by hand the long way, doing multiple derivatives is actually very challenging. It's challenging algebraically. So let's look together at calculating another derivative here. So I'm looking at the second derivative of the square root function. Now we know previously that the first derivative resulted in 1 over 2 square root x. So if I want to calculate the second derivative, the formula for that, by the way, if you missed it, the formula for the second derivative is right here. It's just the exact same as the formula for the first derivative, but I'm calculating the derivative function now instead of using the base function. So the formula for the second derivative is the limit as h goes to 0 of f prime of x plus h minus f prime of x divided by h. And you're going to see my work here looks identical to the work on the first problem. It's just the algebra is going to be a little bit tougher. So here is f prime, and it's going to go right there into my formula. But the other piece of the formula I need to know is f prime at x plus h. So I'll come over here to the side. F prime at x plus h would be 1 over 2 square root x plus h. Okay, so I'm just replacing x in the input with x plus h in the input to get the new function. And I'll color code this as well. So this piece goes with this piece. All right. So let's update everything. All right, so if we stick the pieces into the formula, this is what we get. Now, just a word of advice, when working on algebra problems that have fractions over fractions, you should always try to get rid of the second fraction. And what I mean by that is you multiply by it rather than divide by it. I think we all know that if you divide by 2, that's the same thing as multiplying by 1/2, right? So division is the same thing as multiplication by a reciprocal. So here I'm dividing by h. That's the same thing as multiplication by the reciprocal of h, which is 1 over h. So this term here is identical to what we started with. So algebraically, what we began with and this are the same thing. Instead of dividing this piece by h, I've multiplied by 1 over h. Now, the second thing I would advise here, just looking at this, is I've got a 2 on both these pieces here. I don't want to carry that through all my calculations. So I'm going to actually pull that 2 out and make this 1 over 2h. Now, it's at this point that I'm sort of relying on things I've previously seen in this class. You have 2 things that are subtracted here, and we're trying to calculate the limit. I can't directly substitute in the limit at this point. If you tried to, you'd get 0 over 0 type. Actually, you get infinity minus infinity type in here, but it started out as a 0 over 0 type problem. So it's indeterminate. I haven't canceled anything yet, so I can't actually take the limit. But I've seen this before where we have a fraction minus or plus another fraction, and the technique is to get a common denominator. So I'm going to start off here and I'm going to get a common denominator. So this will be the limit as h goes to 0, 1 over 2h. This is, so the way I do common denominators is you cross multiply and then you multiply across. So cross multiplying gives you square root of x minus square root of x plus h. And then if you multiply across the denominator, you get square root of x plus h times square root x. Now, in this form, this looks like something that we did on the previous problem, and that is this looks like an a minus b term in the numerator. Looks like it's set up perfectly for multiplying by the conjugate. So here in this step, I'm going to multiply by the conjugate. So if I do that, just to save a little bit of space, I'm going to go ahead and put that in right now. The conjugate here would be square root of x plus square root of x plus h over square root of x plus square root of x plus h. And if I multiply that into the problem, remember you square the first term, square the second term, and subtract them. So square root of x squared is just x. Square root of x plus h squared is just x plus h, but I subtract them. And notice how I put that second term in parentheses. A very common mistake that students make is they don't distribute negatives where they should algebraically. So this would be the correct numerator. And then the denominator, it looks difficult because this is multiplied here. Just keep it as is, right? So I'm not going to do anything with the denominator. It's square root of x plus h times square root of x times this piece over here is square root of x plus square root of x plus h. All right. In the numerator, things look like they're finally going to work out for me and cancel a little bit. If you see the numerator, it is the same thing as x minus h. So you need to be very careful here. That negative distributing, you get x minus x, which cancels, but you also get minus h. So the x minus x terms cancel. What you're left with in the numerator is minus h. And in the denominator, I'm just going to keep it once again as is till I'm ready to calculate the limit. All right, it's at this point I noticed that that h that I pulled out at the very beginning can now cancel with this h. So that leaves me a 1/2, and in the numerator, a -1. Okay, this is how I know I'm doing this problem correctly. I managed to cancel the h that I began in the numerator for this problem. Okay, it's at this point that you should try to directly substitute. After you get that h canceled out of the denominator, try to directly substitute. So if I do that, I'll get 1/2 -1 over, substituting in h equal to 0, I get square root of x plus 0 times square root of x. So I got square root of x times square root of x. In this piece, I've got square root of x plus square root of x. So square root of x times square root of x is just x. And then here I've got square root of x plus square root of x, so that's 2 square root x. Combining the 2's in the bottom, we've got 4. And then you've got x times square root of x, but that's x to the 1/2. So x to the 1 times x to the 1/2 is actually x to the 3/2. So this would be the full correct final answer for the second derivative. So this is the second derivative of the square root function. Now, I know that's a lot of work. It's one of the longer calculations we'll probably do this year. You're not going to have anything like this on an exam. Nothing this long, nothing this intense algebraically. I wanted to show it to you because it combined two things that we've done already this semester. That's getting a common denominator, multiplying by the conjugate. But I also wanted to just once again impress upon you that when you use this limit definition formula, most functions, as you take their derivatives, get more complicated algebraically. In fact, some of them are so hard you cannot do algebraically without some really fancy tricks that I wouldn't expect anybody in this course to even have the slightest clue how to get started on. It just becomes really difficult, which is why we need a better way of calculating the derivative by hand than using this limit definition. But it is a good exercise in helping us get better at algebra, so I'm willing to do it once in class like this, but most of our examples from here on out are going to be quite a bit shorter. You're going to see that on the next one. All right. I'm sure you'll probably have to go back and rewatch the video or look at the notes and to pick up some of this, but I'm going to go ahead and move on to the next problem here. What I would like to do is actually use the derivatives now that we can calculate them. And the thing we started the course with was wanting to be able to find tangent lines at any point. And that's what the derivative empowers us to do. I know, from high school, like this is the point slope of a line. So point slope form of a line. And all I need to know is what is the slope. But that's what the derivative tells me. So I will be given, right? You'll be given on these problems, you're given the x value, which is a, and you're given the y value, which is f of a. Both of those come into the formula here and here. right? So there are three pieces to this formula: the y value you're taking the tangent at, the x value you're taking the tangent at, and the slope. So you'll be given the x value and the y value, and you'll use those to find the slope. And we're going to find the slope using that limit calculation that we just got through doing. But we're going to do it for a slightly easier example on this next problem. So this is the final form. This should be memorized. Now, if you don't want to memorize it and you just say, well, I know point slope form, I can substitute out the slope with the derivative, that's fine. But if you prefer to memorize things, you can memorize this tangent line formula, and we'll just have to fill in the pieces of it given the information in the problem. All right, so here is our tangent line example. I've given you a function. So even though it says y equals, we know that this is the function f of x. F of x equals x minus 2x squared. You're also given a point. So I know that this x value is actually the point A where the derivative is being taken. It turns out to be 1. So that's a piece of information we're given. And the other point is the y value, which is f of A, which turns out to be -1. That's the other piece of information that we're given. So I'm going to use these two pieces of information to determine the slope on this curve at this point. So to determine slope, m is equal to f prime at A, but A on this problem is 1, so I'm wanting the slope at 1. All right, and I can use all these pieces to give me the tangent line. Once I'm done, the tangent line will be y minus f of A equals f prime of A x minus A. So that'll be our tangent line formula once we're done. And I already have several of the pieces. So let's start with f prime of 1. By definition, this is the limit as h goes to 0. F of 1 plus h minus f at 1 over h. Now, I think there's probably a couple of you that are sitting there going, I don't know what just happened there. What did he do? Where did that formula come from? Remember, the formula is the limit as h goes to 0 of f of a plus h minus f of a over h, right? That's the formula that you should have memorized at this point. That's the derivative at a point A. So that's the derivative at a specific value. So all this problem is doing is telling me A is 1, so I'm updating the formula to have A equal to 1 here and here. So I'm calculating f prime at 1, so A, the point I'm taking the derivative at, is 1. Okay, I'm just going to come off to the side like I've done for all the other problems here. So f of x is x minus 2x squared. So the pieces I need are f at 1. So I need this piece here. F at 1 is 1 minus 2, 1 squared, or -1. So I'm going to end up plugging -1 into this. The other piece I need is here. And that's f of 1 plus h, which is 1 plus h minus 2, 1 plus h squared. Once again, it's taking f of x and it's replacing x with 1 plus h. So replace this x with 1 plus h and also this x with 1 plus h. And if I simplify that a little bit, it's 1 plus h minus 2, 1 plus h squared. Which I'll go ahead and FOIL that. That's 1 plus 2h plus h squared. So this limit, plugging in the pieces, would be 1 plus h minus 2, 1 plus 2h plus h squared minus f at 1, which is -1. Look, once again, parentheses here are your best friend. Anytime you subtract something in this difference quotient, you should wrap it in parentheses just to make sure you remember to negate it. So it's the negative of -1. It'll be +1 there. If you mess that up, you're not going to get things to cancel nicely like we'll see here in a second. All right, so do a little bit more simplifying there in the top. I'm going to distribute the 2 and the -1. So this will give me 1 plus h minus 2 minus 4h minus 2h squared minus a -1 or +1. All right, if I've done the work correctly at this point, I should get a bunch of cancellations to occur. I've got 1 plus 1 makes 2, but 2 minus 2, that's why it cancels. So all of the constant terms cancel there. Nothing else cancels in the top, but all of the top terms have an h. So you see how every term in the top that's left has an h. I can pull that out. So I'm going to pull an h out from all the terms left in the top. When I do that, I have 1 minus 4, so that's -3. And I have a -2h. So I'm pulling out 1h. I'm left with a -2h. And here you can see that the h I pulled out of the numerator will cancel with the h in the denominator. So I know I've done this correctly. I've reached a point where they cancel. Rewriting the limit. If I now directly substitute in h equal to 0, I get -3. So that's my slope. It's my slope at a equal to 1. All right, once I have that in place, I can then simply update the tangent line formula. So I'm going to go back to the previous slide. And I'm just going to update this formula with what we found. So f at 1 plus f prime at 1 times x minus 1. So that's just this tangent line formula. The point A was 1 on this previous problem. F at 1 turned out to be -1. The derivative turned out to be -3. So f prime at 1 is -3 times x minus 1, because the a value, once again, the a value was 1. So y is -1. I'm going to distribute the -3. So that's -3x plus 3, which is y equal -3x plus 2. So this is the tangent line to the function x minus 2x squared at the point 1, -1. And this sort of brings us full circle to answering the question we started the course with, which is, how do I calculate the tangent line at a point? And this is a big moment in this course because we have the ability to do this now for any function at any point, so long as the derivative limit is defined there. So we have a repeatable way of finding tangents. We've also seen in this lecture today that that way is probably not good enough because the algebra involved can be really difficult sometimes. So we're going to need to come up with a better way of calculating derivatives ultimately, but we have our foot in the door, so to speak. We have a reliable way of calculating a tangent line at any point on a graph where the limit exists. So we're going to do some more work with this on Friday, just to get better at it. And we're also going to talk about the concept of sometimes you can't find the derivative. It's what's known as differentiability. So we'll begin towards talking about that together next week, or on Friday, excuse me. So Friday is our last day virtual. I will return to class face-to-face starting next Monday, but we'll be on one last time Friday virtually here at 9 o'clock. And if y'all have questions this week as you're diving into your homework and the skills quiz, please let me know. Happy to get in touch with you. But otherwise, be safe. Have a good day. See you Friday morning.
And just to make sure, so